Hello, just doing a quick audio check. Okay, everything seems to work. Okay, uh, so it's been like 2 months, I guess, from our last live stream. Okay, this time uh, so last time we actually were talking about CNNs and classification using CNNs, and this time we are moving towards multi-class classification. I think last time we just had quite just we saw the problem statement that what we are gonna do. Uh, so let's start with that, right? This is some scribbling because I was doing something. Okay, okay, I should run the whole thing from the start actually. Hmm. So what we have here is a bunch of images, and images are such that the screen size a little bit. Images are such that uh, you have three labels: label 0, label 1, and label 2. Now label 0 is essentially, give me a second. So label 0 is a straight line. If there's a straight line, then it would be a 0. For example, check this one out: a vertical straight line or a horizontal straight line. That would constitute uh, straight lines and label 0, right? And there is diagonal tilted towards right is 1. So this one is tilted towards the right side, right? So this is 1. So and another one is tilted towards left, that is labeled as 2. So our plan is to just use these. Let's create a generated data set and then run it as well. So our idea is to train a neural network or a CNN network in our case, to do simply classify these three labels. Okay, so this is a function just to create um, these images. So first is the image size and number of images that you want, and other few stuff if you want to go and check it out. So image size is telling you basically the size of the height and width of the, you know, and what is the target. And target is assigned. If it's binary, then it will be like 0 and 1. If it's not, in this case it's false, as you know, because there are three classes, right? It's not a binary classification, it's multi-class classification, right? um, so that's what we're doing here basically. Okay, so it randomly creates these data sets as we are keeping the seed, so you can have reproducibility, right? uh, okay, so let's start with data preparation, right? So this is basically a class to transform data set, that's it. Nothing crazy happening here. We had dealt with this over so many of live streams, right? Just few initializations with x and y, x being the features and y being the labels. Transform is if you have any transformations that you need to do before passing the image to the network, right? And this is for indexing and also applying those transformation, and this is to know the length of the whole uh, data set, right? Or number of rows or number of instance. Okay, so firstly we are taking the images, so just so you know, the images and the labels, right? Okay, so images are there, and let's build a tensor from a numpy array before splitting, right? We are creating this is a this is actually numpy. So we are firstly creating a tensor out of it, but we're gonna be normalizing it, so divided by 255, that's the maximum pixels. We know, so now the range is between 0 to 1. uh, so that is what we did with the feature. In their case, that's the image, right? Use index splitter to generate. So basically now I want to split. So there are 1000 instances, right? So if I were to print that out, images, right? Images, right? Okay, you can see this. This is like the images, right? If I were to show you one of the image, this one being uh, the number is straight, and this is basically corresponding to this line, this label here, the first one. So that's how it looks in an array. Because it's an array, it's an numpy array, we are converting that into a tensor here. Okay, and then we are also converting the labels. So if I were to print out the labels of the one, so this is supposed to have the label of 0. So you can see the label is 0, right? Cool. So that is for the visualization. Okay, now coming to the preparation, right? So we have a splitter. So we had 1000 images, and we want to split it in the ratio of 80 being in the training set and 20 being in a testing set. It's just a simple function that does that. Basically it creates random indexes, where 80 indexes are for 80% of the indexes randomly generated would be for the training and testing. So we are just indexing now. See, we are indexing that over our training set, and sorry, our feature set and our label set. That's it. And we are creating the x train and y train, right? So if I just run it, and actually I can show you how that looks. So now if you see, the x tensor is this, right? It's a, I can also show the shape of the whole thing. Just so there are 1000 instances, and right, and one channel, and the size is h and w, that is your height, and width is 10 comma 10. Now this is a tensor, right? And if I take this, that is train index, and I do this, all it does is it's a generator, right? It's an iterator, we can iterate over it. So I think what we can do here is we can do next iter over the whole thing. Yeah, so you can see it's giving you the first one, right? So that is what it is, one of the indexes. So from the image, I will take this image, this indexed image, and put it in the training set. That's how it's working. It's pretty simple, as it's iterable. That's why we are able to pass it here. And so 80% of the whole data will be turned into your training set. Okay, cool. So in basically this is compose, where we are just telling what to do to the images, basically your transformations, right? uh, so that's a base compose. We have had gone through that normalization has few parameters, that is your mean and your standard deviation, keeping it 0.5 0.5. So using that to in our the created class, right, transformed as a data set, we are passing in the training set, the and the validation set, and also whatever is the transformation we need to do over it. So once that transformation is done, okay, I can also show you what that looks like. I think it would be a train data set, right? So again, it's a, I can clearly do this. Next iter, and you have one of those, right? The first element, which is this. Now you can clearly see one thing, that instead of being from 0 to 1, you have now -1 to 1. That is the range because of this normalization. That's what we did. So I bet you there will be ones here in somewhere, If it's a 1, that means it's something slanting or something. Yeah, you see just 1 here actually. This one was not a really good one to see that, but I hope you understand what I mean. Okay, if you can also just here for in, let's say, train data set, right? I can do that too. And sorry, print out all of them, right? I would not have done that, but just to show you. So you can see here it's a straight line and it's all 1, so it's labeled 0. That's it. Okay, I am gonna delete this. Right once. Okay, cool. So that is how the training data set looks like. Just so that happens. And now the thing is, make balance sampler is basically adding weights to your wire training. In the sense, basically, uh, if there are instances that are imbalanced, that is few labels are in minority and few labels are in majority, so that is what is happening here. It's pretty simple one. You're finding the weights using basically the inverse of the whole count and then multiplying it, and there's a function called weight random sampler. We are just passing the weights into it and the length of the samples and what kind of generator you are. Okay, that's it. So kind of it's a uh, oversampling or undersampling going on depending upon the label, right? So if some label is in minority, we would wanna oversample that. Okay, and finally the train loader, using the sampler in the training set to get a balanced data loader. So if I were to put you this again, this I, train loader, right? Train loader print I. Just break it right here itself once. Okay, you got a few of them. Okay, that's it. Either you can do train data loader, you can do a length on that too. Length operation, because we have said that, right? Train loader. Yeah, there are 50. 50. Why is it 50? Is because in the train loader we have 16 instances, the 16 batch size. What is the batch size? So let's say if I were to do basically 16 is the number of images in one batch, and there are 50 batches, so it should ideally come up to 800, right? So there are 800 instances in your dataset, at least in training dataset, right? So that's why we have the length as 50. Okay, sampler is given. You don't need to sample on the validation set, just training set, so that everything is balanced. All of them have equal representation. Okay, so now let's come into what is the loss function that we are going to use. And here we will just use the board more to understand what's happening here, right? So I have already done few things. So this was the architecture for the LayNet. I guess AlexNet or LayNet we were doing before. Okay. Um, so let's talk about softmax a little bit. Softmax is this simple function, okay, which basically, if you have here C tells you number of classes in your data set, right? Right now there are 3 classes. So whatever comes out of your let's say you have this one is there, right? This logit is there. It's a random tensor. We're just demonstrating how it works. Okay. So in that case, in the binary classification problem, the models would just produce one logit, right? And that one logit only for each data point, right? So it makes sense to use a simple binary classification where you have a 0 and 1. You just wanna with that one logit you can handle everything. But now the logit outputs representation of what? Log odds ratio, right? You remember? So the so answering yes to the question above, that is how does a given data point belongs to a positive class? Given that this is the basically we see the sigmoid of the whole thing and then say normal, there's no need to normalize if there's just one, right? So we know it's between 0 and 1, and if the probability is higher than some threshold value in the sigmoid after sigmoid function, we know that it's in the positive class, right? Yeah. So there is no need for to pose, so there is no need to pose any other question to make the decision. We just use sigmoid function to map our logits to probabilities. So that is it. But in multi-class classification, it's way more complex. That is, uh, we need to ask one more question. That is, we need to get log odd ratio for every possible class in this case, right? In other words, we need as many logits as there are classes. If you remember in our system that we had, if I were to, sorry, yeah, let's work here. So in our system, if it's a simple binary ones, right, I'm gonna use a little darker one. Yeah. So if there's a simple binary one, all you have is one logit and one logit coming up, right? It's going in, and this is outputting. This is a sigmoid function, and this is if it's beyond some threshold, let's say 0.5, then we say it's, if it's above, then it say yes, or if it's lower, then we say simply no, right? That was as simple as it could get. But now in multi-class classification, you need to have uh, as many logits at the end of the network as you have the classes. If you, in our case, what it would look like is we have 10 input points, right? 10 input points, and with some network, suppose, and then here at the end you need to have three outputs. Now this three outputs is representing one class, so this might be representing, so if I were to zoom in, this is representing your basically uh, 0th class, or this is your first class, this is your second class, that is, this is a straight line wala, straight line, this is your tilted right, I'm just gonna right, and this is your left, right? Okay, so these network, when you connect this, so this is how it should be. At the end of the network, you need to have as many logits as there are classes, so that you can make this multi-class classification. Okay, you know, the problem, that one thing is that a sigmoid takes only one logit, right? If you know, sigmoid function is simply 1 by 10 e to the power minus x, right? So it just takes one parameter. Okay, so I guess we need something else to get this probability right. So that's where the softmax come into play. So softmax function return for each class the contribution that a given class had to sum of all ratios. So the basically what it does is, a class with a higher OR ratio will have the largest contribution, as thus the highest probability. So let's see how softmax works. So softmax has this simple formula that is that looks like this. You have to take the exponent of everything. Like for example, in this scenario in the code, let's see, there are three what do you call three so let's suppose that this is the output that you got from the last last three nodes of your network, right? Or the output of your network. So there are three of them, right? That's what we are representing here. So 1.3, 0, and minus 0.6. This is the thing that you got out of it. Now the first one representing label 0, second one representing label 1, and third one representing label 2, right? The first thing that you have to do according to the softmax formula, that is, you need to have e of all the ones. So if it's in this case it's z0, and e of z1, and e of z2. So that's what we are going to find now, right? All you have to do is as for a tensor, that is this logit, if I put an exponent, put in the exponent function, all it does is it takes the exponent of each of them and spit out a tensor that is of the same shape but is has done that exponent. Okay, so if I were to run this, you will see it's 4. And if you want to just verify, so if I do this, e to the power of, let's say, 0, so that is 1, of course, and that's what you get here, right? E to the power of 1.3863, right? That's 4. Okay, so that's what we just did. So basically in our situation, as what are the z's here, then in our situation, okay, this acts weird sometimes, I don't know. Okay, here we have the z's as, let's use a different color, I guess. Okay, so the three z's, z0, z1, z2, this is 1.3863, 0.0000, and minus 0.6931. And if you put it here, so this is giving me output of 4, this is 1, and this is 0.5. So this is what you got. Now you have 3 of them. Now what softmax tells you to do is simply, according to the equation, that you do basically take every one of them, okay, and summation of all of them, right? E to power z, and c goes from u0 to basically the number of classes that you have, right? So in simpler terms, if you expand this whole thing, it would look something like this. E to the power for the first one, we are trying to find for the first one, so this one, right? E to the power z of 0 divided by the summation of the whole thing, e to the power z of 0 plus e to the power z of 1 plus e to the power z of 2. That's it. So this is for the first one. Second one, it would be simply e of 0, e to the power, again the whole thing, right? 1 and 2. Again for the third one, e of c2, again the whole sum would come here, right? This is what we are seeing here. So that is what I have written here itself. So you just add all of them. Okay, so softmax for the 9 would be like 9 putting everywhere and the sum of this, and so you create this tensor. That's what we will be doing soon. So you just created the exponent versions of the logit, and now this is basically your softmax. That is your odd ratios that we have. Odd ratios are basically the exponent value of the logits, right? And you're taking one by one. So if you run this, that's what we are getting. You can clearly see what. So if I were to show you the sum of this, it looks like this. And if you want this exact value, all you have to do is take the first guy, that is your 4, right? Let's take 4, paste it here, and let's do this. You get the same value for the first one, right? And for the second one would be 1, and that's for the second guy. So that's how you got all the so in the single way. Now this is your softmax, and if you do a summation on it, you can clearly see it will always add up to some, because this is a probability. So now we were able to map the whole of the logits that got here, as this doesn't add to 1. You can clearly see there's a negative sign also, right? So anyway, we want to do a probability representation of the whole thing. So now you can clearly see that the whole thing adds up to 1, right? So now we have what we would call a distribution, right? So this is a distribution. So for one input image, if your model is predicting, sorry, okay, so if for one input image your model is predicting this exact value that we just took, so now we have a distribution, right? So what is the distribution? It's 0. What is the distribution? It's 1. And what's the probability basically? And let's say probability is, this is your 1, right? Probability. And your classes. So you can clearly see, and the first one it says is 0.7 somewhere here, right? That much. This is the one. It is 0.1 somewhere here, and it's 0.0. Oh my, that's not even go. So we can clearly see, mm, according to our model, for that logit output, the highest probability of it is being in the 0th class. So okay, so it's probably a straight line according to our images, right? So that's what we will be doing, right? So now our task is also to create loss function out of it. That is, loss function is uh, stating, quantifying the error in your model. So you pass in an image. Let's say you pass in an image, and it was actually tilted towards right or something, but your model gave me this logit, and if with that logit I am concluding that it's 0 as of now, right? So if it's concluding that it's from 0, that is, it's a straight line, then there's a problem. That is, our model is not working properly. So I need to formulate a loss function that will take in account of this error and then minimize it. Okay, so here they have just given basically a softmax function that you can directly apply. So here it's pretty simple. That is, you can use nn module or you can use the f module. Both of them will work. nn module will has the same name, softmax, with a capital S, and whatever is the last dimension, you have to do it on that and pass in the logits. Here also you're passing in the logits and telling it to apply it along the last dimension. Okay, so that's how it's happening. Okay. Cool. So you can see the values are same. Okay, so now let's get to what our negative log likelihood loss. Probably I will be able to break it down. It's not that crazy. It's actually pretty simple stuff. uh, don't go for all these equations, but rather just have a look here. So in our situation, when if we had a normal binary cross entropy, that is your binary loss function, right? It's simply, this is the formula, right? If you, pretty simple, that is, you are averaging the number of counts of the instances. So this would be total data set. In our training set it would be 800, so 1 by 800, right? If it were a binary classification task, okay, so you have a log of the probability, right, uh, of something, and then also the log of that it's not that. So you also multiply, I forgot to add that, you also multiply the actual value here, right? And this is your predicted value. So this is your predicted value, right? So I'm gonna put like this or something. Okay, yeah. So that is how it mostly looks like. uh, hmm. Okay, this is actually, mhm. Yeah, this was another style of equation, keeping it same. So we don't need this here. In this case, there was one more implementation that you can use in. Okay, so if what if there are more than that? So you can convert this whole loss function into, so there are three instances, multi-class instances, right? So there are n0, n1, n2, and so in that case, all you have to do is, instead of having this, you can clearly have this over it, right? So now you have simply number summing over the number of instances with label 0, what is the log of that probability. Okay, probability that that instance is 0. For in our case, um, the probability, it spit out the scenario that we were in, that is, the actual image is tilted, but our model is saying it's not tilted, that it's a straight line. So that probability is much higher, so this would be a higher value, right? Cool. And if this is a higher value, right, what happens is, if you know how a log graph looks like, a log graph looks something like, use this. Okay, like this. Okay, a log graph view looks something on this line. So it goes from, let's say 1, and this is your log graph. Plot log, right? So it goes infinity towards the bottom. So anything that is from 0 to 1, any value that is from 0 to 1 will always be a negative value, firstly, right? Also, it's gonna be, so if the closer it is to 1, the smaller is the value, and further it is from 1, that is it's approaching 0, the value is rising exponentially. Okay, so in our situation what we had was, our model is saying that the actual label was, let's say 1, and our model is saying that the label is 0, right? Our model is saying the label is 0, so this is giving high probability. So it's, let's say 0.9 something, it gave the probability, or in our situation it was 0.7, right? It was 0.7 something, yeah, 0.72, 0.72, it's something like that. Ideally it should have given this guy as the highest one, right? Because it was right tilted. In our scenario, actual image is this. Okay, so now we know this is the scenario, right? And if I take a log of this guy, if I take the log of this guy, it would be somewhere here, right? So it will approach this guy. So this is the y value that we get out of it. The loss value would be this, right? The prob so if you take the log of that, okay, so that is, till now we can understand what this function is doing. Okay, okay, so in for that instance, uh, okay, let's go on and actually code it out so that we have a better understanding of the whole thing, right? Formulas are pretty simple. So if I were to show you what it is, you have the logits. These are the normal logits that's coming from there. If I just to give you the values, this is the value for the logits, and okay, sorry. So logits are being passed to the NN function for softmax. So we are doing the softmax is done. So softmax version is there, so you can check the sum. Okay, it's 1. We are converting it to NumPy just to show you how the calculation is happening behind the scene. So converting NumPy and using NumPy to do a log. This is a natural log. Okay, just to check that if it's natural log, I'm showing you. If it's 100, if it was some other base, it would be something else, right? So it's a natural log, and what you're doing is you are taking that softmaxed. So softmaxed is basically, it's a probability distribution. It adds up to 1, right? And you're doing a log on that. So basically this operation that you're logging every single instance from inside it, right? If you do a log on that, so you get this value. So if I were to also show you on the terminal, so if I do ln of, let's say the one was 0.73 something, right? So you can see it's minus 0.14. So that is what we got, minus 0 point, sorry, it's 31314. So that is what we got. Of course, it was a bigger value. So that is what you got. Okay, 31 is what you're getting. So you did a log on the softmax. Now all you have to do is, okay, so this is what we will be doing. Okay, so there's a simple function already inside F module in PyTorch, that is log softmax. All you have to do is call that function over the logits along the last axis, and it will spit out the same answer. So you see this one, compare it to this one, and it's actually the same one, right? Okay, so you can clearly see this is in the dimensions only have been changed. We are adding one more dimension into it. Okay, okay, so this is, instead of a vector, it's now this is a matrix, like a 2D tensor instead of a 1D tensor, right? Okay, so now if we do a log probability sum, this again adding to 1. Okay, just so you know, once we are done that log operation on all the elements, it doesn't sum to 1. Okay, Okay, let's say the label is 2. Okay, now let's say the label is 2 and the label we are passing here, okay, to our actual one. So what it does simply is will get know that soon. It goes to the second index, that is this one index, and multiply and sorry, basically takes that index and spit it out. You can clearly see that, right? Second one is taken because that was the original value. I want to know how is that performing, right? So I know the log probability here is 0.9 and it has been spit out. Okay, you might ask what is the point of this. So basically this is your loss function. As of now we are taking what is it giving this guy. We know the probability is, sorry, the label is 2, so this was supposed to be 0 actually. This was ideally it should be 0 because it's a loss, right? So there shouldn't be an error, but we clearly see it's not a 0. That means we have to optimize it, we have to bring it lower. Okay, so we will do our own implementation of the uh, negative log likelihood. So the negative part, I hope you understand, we add the negative part here in the start of the whole thing because logs make everything in the negative because of the range they have. This is always negative, we just want to neutralize it, so we add one more negative into it, right? um, so that's where the negative and log likelihood is basically you're taking the log of the probabilities. That's why it's log likelihood. You know, probabilities are not really likelihood, but okay, for our use case it is what it is. So we were gonna build the same thing but here using simple mathematics, right? And code. You can go through this. Basically it's here it's just one instance, so doing this will give you the tensor. This is coming from here. What is the total count of the tensors, um, right? And then what is the log probability that you have? This is a negative log, is basically this. So you can clearly see the formula is important here. The formula is stating that negative of torch sum all the log probabilities and then total. So basically this whole operation is exactly this operation that you see here. Here the summation is happening, right? This summation inside part, the inside the bracket, that is what's happening here. Okay, we will understand it through a bunch of what do you call, matrices. So you can clearly see if so the actual label was to, one thing you'll notice here is the actual label was 2. So this guys are basically down to 0 because they are not being considered in the loss function. This guy and this guy is not considered, just this guy is considered in the whole equation, and that's what we get. That's why we get 0.3 point something, right? 0 minus 2.3. Okay, because we know the labels and we are supposed to reduce this loss rather than, they don't have nothing to do with it, right? So this part is where we are supposed to be focused upon. That is what's happening. So in this case also you can check it out. If you have, let's say there are 5 images, okay, and the first image the true label is 0, the second image true label is 1 and 2 and 0 and 1. So basically the first image, ideally your model should have a higher probability for this value, you know. That is your 0th label. So this is a true value, this is your logits that you got out of the model. Okay, so we're gonna do something that's pretty simple here. That is, you are passing in the y predicted and uh, the true values, right? And we are taking the total count. So here in y true, here is you will know that it is 5. There are 5 of them, right? So that is there. So extracting the log probability corresponding to true class labels is simply taking the log probability of the whole thing. That is arrange is basically going from 0 to total count is 5, so 0 to 4, right? And so 0 to 4, and you can clearly see of this y true. So what it does is it says first take 0 0, okay, 0 for the 0th value, for 0th value from the y true is 0. So this value has been taken here, right? Because our idea was to, um, if it's if you know the true values, if you know the true labels, that is 0, I want this value inside, right? If it's 1, then I want this value here. If it's 2, then I want this value here, right? If it's again 0, then I want this value for the fourth image. If it's 1, then I want this value. Okay, so that part has been taken care of. If you check this out here, as I'm putting it, you can clearly see this is the zeroed index for the first image and the output of the first image, right? The logits for the first image, and this is for the first index or second index, right? In the second image logit. So is for the other guys, right? So I hope that made sense, that we are focusing upon only the ones that we know is relevant to the part. So that's what it's doing, creating log probabilities and then just summing them up, just summing all of them up and a total count. So that is what it is. Okay, so you can clearly see this is the final loss that we got in this situation. Okay, and if we were to use the PyTorch implementation also, fnn loss, and you are passing in the ypred and ytrue, which is coming from here, ypred, these are the 5 images, and what is the ytrue, right? And you can clearly see both these values align with each other. So that was an implementation of negative log likelihood. So I hope you understand how it's taking things that are only relevant to the whole image. Okay, give me a second. Yeah, okay, going back to okay, so few things is that nothing much. Okay, now there is one more, just so you know. So there are a few arguments that you can pass actually in the negative log likelihood. That is here, basically there's a reduction and the weight matrix is there. Okay, and we will see into how that works here itself. Okay, let's create a new dummy logit here. Okay, this is your a matrix of 5 by 3. It's a big matrix with basically it would be like 5 images, and 5 images output would be 3, right? I'll just show that. Okay, I haven't run this, so you can clearly see this is the logits that you got for the first image, second image logit, third image logit, and all that stuff, right? And then you have the actual labels. Again, you're passing to the softmax function the logits, right? The actual logits, and what it does is take the softmax and then take the log of that too. Okay, and you have the dummy log probabilities and dummy log logits as well. So I'm gonna delete these guys, and now you can do the same thing that we did there here itself, simple code. So relevant log probabilities are these ones, because see, the first is the first image, the actual label is 0, so I am supposed to, from the log probably I am supposed to take this one, that has been taken. For second one also it's 0, so this one is the one that's relevant. For the third image it's 1, so this one should be relevant, so that's what's coming here. That's what it did, and did a mean on it. That's what happening. So you can clearly see how it's working. So if I do manually or using the nn dot this, you can clearly state that. Now there were a few parameters, right, inside it, as I told you, optional parameters that are reduction. So it takes either sum, mean, or none. The default is mean, corresponding to the equation that we have here on the right side, right? So as expected, sum will just return the sum of the errors instead of averaging. The last option, none, correspond to the unreduced form, that is it returns the full array of errors. This just returns the array instead of doing any aggregation function on it, any aggregated uh, output, right? So that's what that is. The weights also, so it takes a tensor of length c that is containing as many weights as there are classes. So if you want to weight balance, this argument can be used to balance basically imbalance data, unlike the weight argument in the binary cross entropy, right? Also, unlike the position weight argument in the binary cross entropy with loss, a logit loss, the negative loss likelihood, right? This function computes true weighted average when this argument is passed. Okay, so we can just pass it through. We can clearly see the difference in how the loss is changing. It was the loss here, but I'm adding uh, twice the weight to the last label, so uh, the loss has kind of changed, and you can ignore also a few indexes. You can completely ignore them. That is the second index, whatever is the second index, I don't need it. If there is anything with the second index, let's say this one, I guess if I were to, let's say, remove this from here, you will get exactly that point, right? Cool. And if I were to take this for all third ones, I am doubling it. So can we like double it? Um, can we like double the third one? So basically the 2 1 has to be double. I can just twice the thing. Okay, I'm missing out on something, I guess. Um, I think there is some ambiguity how exactly it works, but it does give more weights to the this particular ones. I guess the weights are given before the whole thing, maybe. Okay, so let's get to a more general approach to the whole thing, that is your cross uh, entropy loss, right? Okay, that's done. So the formal loss function took log probabilities as an argument together with the labels, right? That's what we gave. First we took the softmax and then we did log on that. So basically the log softmax. So the log probabilities were the input with the labels that we had. Okay. So now there's another option that you have where you can just push in the logits instead of passing through another log softmax and then passing through loss function. Rather than just take all the logits and pass it right away. So this is just like what we saw in the binary cross entropy with, there was the binary cross BCE loss and there was BCE with logits loss. So in BCE loss we had to first convert into some kind of a distribution then pass it, but BCE with logit loss you can just pass in the logits and it does behind the scene, right? So it means you should not add a log softmax as the last layer of your model when using this loss function, that is your cross entropy loss. This loss function combines both the log softmax layers and the negative log likelihood loss into one. Okay. You must see the right combination of the models. For example, um, log softmax as a last layer, meaning your model is producing log probabilities, combine it with NLL loss. Okay. And if you are not using the log softmax as your last layer, then combine it with cross entropy loss. Okay, so mixing log softmax and cross entropy is just wrong and it won't work, right? Now that the difference between the argument is clear, that it's take a closer, so let's take a closer look in the cross entropy, right? So there are a few parameters that you can pass. Here you can see this is again the same thing. I'm passing in the same thing. You can clearly see this answer and this answer is same using the cross entropy loss. Okay, nothing crazy happening here. There are a few arguments that you can pass here actually. If you see, there is an argument called weights. There's a weight argument. The weight argument takes a tensor of length C. Again, the weight same argument. The reduction also is the same. It has default is mean, and basically uh, has the same arguments that you have, sum, mean, and none. And ignore index works the same way as the other ones, right? So nothing crazy here. So let's actually now build our configuration, and this time let's build a convolution neural network for real. Hmm? So this one is pretty simple. We will be doing our images that we have right now is 10 by 10. So uh, you can clearly see in our case we are using a sequential model CNN1, and the first module that we are adding to the sequential is con v1. So for the first convolution layer, which is a con 2D layer, and the input is channel is 1 because there's only one channel. There's, if it was RGB it would be 3, right? It's just a grayscale image, and the output channel is the one we define it to be. So output channel would be, let's say here it's 1, okay, and the kernel size is 3, and then we are passing it through a ReLU for activation and the max. So the size would go from 10 to 8 to 4 after this first block, this whole thing, okay. That's how the size is changing of the image, okay. And the number of channels is 1 anyways because it's, we are defined the output as 1. Okay, and then you are straight away flattening the whole thing. Now flattening the whole thing is basically taking this final value and putting, as this is a matrix, it putting into a straight up array. Okay, so it will be, there will be 16 numbers in an array, right? And now this is a classification part. So this is your featureizer block where we are using convolution. We are taking the features out of it using convolution layers. Now we are just doing classifications. So in the last layer we have in the last layer we have FC1, that is your basically linear network. So if I told you there are 16 of these guys flattened, so that's what you 0 to 15, and then there are 10 of this hidden layers. So that's what happening here. The input is of course the number of channels into 4 into 4, number of channels being 1, so it is 1 into 4 into 4, that is 16, and the output feature is 10. Okay, so that's what you see here, and that this is your activation, ReLU activation, and ReLU operation does not change the size of the vectors whatsoever. And then you pass it, and the final output input is again 10 because this is coming from 10, and the output is 3, so this is a 3. So as I told you, multi-class classification requires as many nodes as there are classes in the last output layer. Okay, so that's that, and simple stuff. We are just putting it into a training situation. We are okay, sorry, I did not run this. Okay, so we are using cross entropy loss with reduction of mean, and the optimizer is SGD there, and the model parameters, whatever the parameters are, right, and the learning rate we defined. So we are printing out the model. This is how the model looks like. We can also see the parameters inside it. Okay, that's that. You can also see what is exactly the parameters inside. So bias term for the convolution 1, whatever it is, or you can just copy this one and put it here, and there you go. Sorry, and this is, so this is the kernel, right? This is a 3 by 3 kernel, so that's why you had 3 by 3 matrix. Or cool. So let's train the model, I guess. So this is your step-by-step training method, and train it for 20 epochs. All right, 20 epochs has been trained, and then you plot the graph. Okay, that is the model, and we are just training it to do the task that it's supposed to do, that is to classify the images, right? It's taking much longer than I thought. So this is the basically the final graph that you have. So this is your blue one is the training loss, and the red one is your validation loss, right? And you can see validation loss are pretty good, considering the ANN network that we created for image classification in the previous classes or live streams. Okay, so this was how the whole thing works. And let me just check with my. It's been 55 minutes already. Okay, soon we will be next sessions would be over uh, visualization of these filters that you have inside the, so in this whole system. If I were to draw this whole system, and then I will take a leave. Okay, so this system is, if I were to just draw this. Okay, so firstly you have an image. Oh, firstly you have an image that is 10 by 10. Okay, now that image okay, there's a 10 by 10 image, and then you are putting it through a single kernel. In this, with the, if you remember, the input channel is one, input channel is one here, and the output channel is also one. Okay, so we are just passing it through one kernel or one filter. So it will be like this, just one filter. That is, I'm gonna draw it smaller because it's 3 by 3, right? So I'm just gonna small it. 3 by 3, 3 by 3, right? You have this big image, some image, right? In this case, let's say it's like this slanting line, and you're passing it to one kernel. Okay, so now you are, after it's passed through this kernel, you get an output which is a little smaller than the previous one, that is 8 by 8. Okay, and you pass all the things from a Relu activation. I'm not selling this, but I just added here. Relu is also added, let's say, and then this whole thing is passed to a uh, max pool, right? Max pooling will literally shrink it into 4 by 4 matrix, right? So 1 2 3 1 2 3. So this is your 4 by 4. The image that you had here, this is your kernel. So I'm gonna maybe shade the kernel or something, right? This is your kernel, right? Okay, so filter, cool. So, and this is the image, this is the image being transformed. So finally this is your feature output. And then what you do is you take this, you flatten it. That is, every single pixel is aligned in like this. This one goes here, and again and again and again to flatten. This is what you call a flattening of the whole thing. So as these are numbers, so it is basically an array, and this array size is 16 elements are there. Okay, now you take the 16 elements, you line them up as inputs that you see here, this whole diagram. Then the whole this whole diagram comes into play. So I am just gonna maybe copy this, I guess. Can I do that? Maybe I cannot. Okay, that's fine. So then you have these 16 of them. Okay, 16 of them going to then 10 of the other neurons, and then 3 of them. This is how the architecture is going. I hope you can understand everything from here. Your image is there, your filters are there, image is there, right? Filters are there. uh, what is the output from the first con? So this is your whole con, right? After the convolution, is this is the image. Here the max pooling is happening. Let's call it max pool, and then flattening, and then this whole thing is passed into an ANN, artificial neural network, a simple ones with a lot of connections and stuff, right? There's a absolutely, there's a ReLU over here also, and then you have 3 logits. Okay, so this is your Z1, the ones that we saw. Okay, that is how the architecture is. Now the next part that we are going to do is simply to visualize what's happening to this. can we visualize what is happening after this convolution took place, or after this max pooling took place? So that is what we're going to do, visualizing the kernels. Okay, so you will see that too here. Okay, you're going to learn about hooks, what are hooks and how hooks are used, and how we can actually see inside the model and every parameter that is inside the model. Okay. Okay, so that is that for this live stream. Thank you for joining.